problem F6-8. Determine the force in members LK, KC, and CD of the Pratt truss. State if the members are in tension or compression. So if we look at the figure, we can see that LK is this member, KC is this member, and CD is this member. Which means that we can get all three members with a single cut if we make a cut between LC and KD along this angle. That will give us two subsections. There is this triangle right here, A, B, C, and L, and there is this larger trapezoid, K, D, G, H. Now, one thing we might notice is that with three members connecting these two subsections, that is three unknown forces, both subsections also have reaction forces, which means that we can't solve with a single cut's worth of equations. Now, my thinking is that because there are three cut members right here, if we could find these reaction forces, then we could use just a single section to solve for the remaining cuts. There's no reason why we can't use the truss as a whole as our section. So with the truss as a whole as our section, there are no tension forces, but there is the reaction forces at A and the reaction force at G. So I've called that section 2 here. So I set it up. The sum of forces in the x direction, well, reaction G is a roller support, reaction A is a pin support, so reaction A is the only one that'll have an x component. There are no x components of load forces, which means we can say that reaction at A in the x direction is 0. For sum of forces in the y direction, we had the y component of the reaction at A, we had the reaction at G, and we had these three load forces that add up to 90 kilonewtons downward. So our equation there, RAY plus RG minus 90 kilonewtons equals 0. And last, our sum of moment equation, we should pick a point of rotation. I picked A. That way I would get rid of both AX and AY in unknowns, meaning the only unknown force would be the reaction at G. So in the A, and for direction I'm going to rely on the right-hand rule, these three load forces will create a negative moment, or a moment that would cause it to rotate clockwise. Whereas an upward reaction at G would create a positive moment, or cause it to rotate counterclockwise. So putting in all the numbers, that gives us negative 2 meters times 20 kilonewtons, minus 4 meters times 30 kilonewtons, minus 6 meters times 40 kilonewtons, plus 12 meters times the reaction at G equals 0. So to solve, I'll start with this one. Reaction at G is our only unknown. If we plug all those values in, we get that the reaction at G is 33.3 kilonewtons. At A, AX is easy because the reaction at A in the x direction is 0. And once we know the reaction at G, we can plug that value into here and find that the reaction at A reaction at A is 56.7 kilonewtons. Now we can go back to one of our cut sections. I selected this section. If you're following along in the book's guide, it looks like they were using this section, but either section will work. So looking at this section, the triangle formed by ACL, forces in the x direction, remember we've cut along here, there is the reaction in the x direction at point A, which remember we found was 0, the tension in LK, and the tension in CD. So that gives us an equation RAX plus TCD plus TLK equals 0. In the y direction, we have the y component of the reaction at A. We have Kc is a cut with a vertical component. And we have the 20 kilonewton and the 30 kilonewton load forces acting on our section. So that equation becomes RAY plus TCK minus 50 kilonewtons equals 0. Lastly, moment. Now I selected moment at C because that would eliminate the unknown value of tension CK and tension CD. The only unknown tension would be the tension LK. So if you do that, the sum of moment equation becomes negative 4 meters times RAY minus 3 meters times TLK plus 2 meters times this 20 kilonewton load. Again, the 30 kilonewton load, tension CD, and tension CK all have no moment arm. I should also explain that even though the tension in LK is acting on point K, I can still use this distance right here, the 3 meters, because the tension LK is acting purely in the horizontal direction. And as far as moment is concerned, you are allowed to move the force along its line of action to any point that makes the problem easier to solve. So solving for these, first we can solve this formula for TCK because RAY is known. RAY was 56.7 kilonewtons, so TCK must be negative 6.7 kilonewtons. Next, we can use the sum of moments equation to solve for TLK because, again, that is the only unknown in that equation. And that gives us TLK is equal to negative 62.3 kilonewton. Lastly, the sum of forces X equation, again remember RAX is 0. That means TCD and TLK must add up to 0. So TCD is 62.3 kilonewtons. Last, recall that we have assumed everything is in tension. So if there is a negative, that means it's compression. So our answer is TCK is 6.7 kilonewtons of compression. TLK is 62.3 kilonewtons of compression, and TCD is 62.3 kilonewtons of tension.